Welcome back. So we just took a look at sequences. Now we are looking at series and a couple of specific types of series. So a series is when we take like a sequence, like here's a sequence, and this is our addition sign. It means to add it all up or to sum. So we're adding all up all the terms of a sequence. All right, it is the sum of an infinite sequence. So it is infinite if we're doing something called a series. All right, so we can say that a series converges if the sequence of its partial sums converges. So like we sum them up, like the sum of just the first term, and then the sum of the first two terms, and the sum of the first three terms, and the sum of the first four terms, and so on, all the way to the sum of the first n terms. And if this sequence has a limit, as n goes to infinity, then we say that the sum converges. All right. If it doesn't have a limit, then we say the sum diverges. So the sum of a sub n would diverge. All right. And this is how I write my sum. It's just very quick. It's just kind of squiggle, squiggle. All right. So I don't try and make it fancy looking like that. So find the sum of each series if possible. So let's just look at the sequence here that we can make of the partial sums and see what happens. So if we plug in 1, we get 1/2. If we plug in 2, we get 1/4. If we add those two together, so the first, so these are the terms. These are our a sub n, and this would be the sum. So the sum here would be 1/2, and then it would be 3/4 if we add those together. The next term, if we plug in 3 here, we're getting 1/8, and we're starting at 1. So 1, then 2, then 3. So we add an 1/8 to that, to 3/4. I believe that gives us 7/8. Our next term is 1/16. So if we add a 16 to 7/8, so this would be what, 14/16 plus another 16, so that'd be 15/16. All right, then we got 1/32. So that'd be 30/32 plus 1, so that'd be 31/32. And this would be 1/64th, and this would end up being 63/64. So it looks like this is just going to be like 2 to the n on the bottom, and this is 2 to the n minus 1 on top, which looks like that will go to 1. As we go to infinity, this minus 1 won't do anything. All right, so this sum, we think, is 1 at this point. We'll go over how to find it here in a couple of minutes. All right, but we're just kind of exploring here. All right, so now for this guy, let's try this guy. So it's got two terms, 1 over n minus 1 over n plus 1. So if I plug in 1, I get 1 over 1, 1 over 1 minus 1 over 2. There's my first term. Next, if I plug in 2, I get 1 over 2 minus 1 over 3. And if I plug in my next term, I get 1 over 3, keep wanting to get ahead of myself, minus 1 over 4. And the next one's going to be 1 over 4 minus 1 over 5, and so on. So if you look what happens, if we just drop the parentheses, these are going to cancel out. These two are going to cancel out. These two are going to cancel out. This with negative 1/5 is going to cancel out with the next term over here. And what's going to end up happening is we're going to have 1 from this first term, and then we're going to end up having minus whatever the last term we write is, 1 over n plus 1. All right, because the first term always cancels out with the previous one, and if we stop at some point, we're going to have that last term still. All right, and if we take the limit as we go to infinity, this is just going to go to 1 because this part goes to 0. It's going to be 1 minus 0, which is 1. So this guy definitely converges. This guy did too. All right, let's look at the last one here. So this one's actually the easiest one of the three. So if we start looking at the sum here, so we'll have 1 plus 1 plus 1 plus 1 plus 1 plus, and so on. So our partial sum, so our nth term sum would just be n, right? We had 10 terms, it'd be 10 ones, we'd get 10. All right, so if we do the limit there, as n goes to infinity of n, that goes to infinity. So this guy diverges. As a series, it diverges, right? If we're adding up stuff, it diverges. If we're just looking at the sequence of 1, the sequence converges. So they are two different things. Make sure you try and keep them straight there. The sequence would converge, sequence of this guy, because it would just be 1 always. But the series, when we're adding them up, that diverges. All right, the first specific type of sequence that we're going to, or series that we're going to look at is called a geometric series. All right, it is the sum either from 0 or 1 to infinity, or actually it can start wherever, of some number times a common ratio raised to an exponent. All right, so this is our ratio here. All right, it's going to converge. So this thing raised to the exponent n this sum will converge as long as that ratio is between 0 and 1. All right, as long as it's a fraction or a decimal. If it's less than 1, it will converge. If it's greater than 1, it will diverge. All right, think about it. You have like a big number here, like 2 to the n. It's just going to keep getting bigger and bigger and bigger. But 1/2 to the n will keep getting smaller and smaller and smaller. All right, this a, we're calling a, that's just our first term. And r is what we call the common ratio between two terms. So if we just divided between any two terms in that series, right, that would give us r. Like a r to the n plus 1 divided by a r to the n. The a's are going to cancel out. We have one more r on top. We just get r. All right, so the sum, if we wanted to know the sum for this, it is a over 1 minus r. Or think about it this, the first term over 1 minus that common ratio. And that will give us the sum of that series. It's kind of neat. All right, so if we've got this guy here, let's see, we could say this is 3 times 1/2 to the n, like that. All right, so now what we can do is say, okay, well, what's our first term? So when n equals 0, we get, if we plug in 0, we have 3 times 1/2 to the 0. 1/2 to the 0 is 1, so we get 3. That's our a. What's our common ratio? Well, it's the thing in the exponent, the thing being raised to the n, so our r here is 1/2. So since that's less than 1, that tells us it converges. All right, and then the sum would be our first term, which is 3, over 1 minus 1/2. So 1 minus 1/2 is 1/2. We get 3 over 1/2, which is going to be 6. All right, 2 times 3, 6. All right, let's try the next one here. All right, so let's see. Our first term here, well, let's actually, we have 3/2 to the n. Our first term would just be 1. Like if we plug in 0, we get 3/2 to the 0. That gives us 1. That's our a. All right, but our r here, the thing being raised to the exponent, is 3/2. That's greater than 1. That tells us that it diverges. All right, if r is greater than 1, it diverges. All right, so we can't find the sum. The sum goes to infinity. All right, we keep adding bigger and bigger things. This would keep getting bigger and bigger numbers. It would go to infinity. All right, what about this guy? So now the trick here is it starts at 4. So our first term is when n equals 4. So if we plug in 4, we get 1/2 to the 4th. So 1 to the 4th is 1. 2 to the 4th is 16. That's our a. Our r here is what's being raised. It's 1/2. That's less than 1. That tells us it's going to converge. All right, so that means our sum is equal to 1/16 over 1 minus 1/2. So that's 1/16 over 1/2. 2 times 1/16 is 1/8. So our sum is going to be 1/8 if we add up all these terms. All right, before, on the other slide, we had 1/2 to the n. We were doing the sum from, I don't remember if it was 0. No, it was 1. We were going from 1 to infinity. So our first term there, our a would be 1/2 over 1 minus, our r would also be 1/2. So we'd get 1/2 over 1/2, which is 1, which is what we guessed it was going to be. All right, see, right here, we guessed it was going to be 1. And now we have a formula that tells us that this does equal 1. All right, so that was the geometric series. The nth term test for divergence. So this only tells us if something diverges. This doesn't tell us anything about converging. All right, if a sum is going to converge, then its limit has to be 0. Like those numbers at the end that you keep adding have to go to 0. But just because it goes to 0 does not mean it converges. So this doesn't work backwards. So if the limit equals 0, that does not mean that the sum converges. All right? That's the biggest mistake people always make. Just because the limit equals 0 of the sequence does not mean that the sum, the series, will converge. Not. All right. However, if the limit does not equal 0, then 100% sure it will diverge. All right. So if we take the limit here, limit as n goes to infinity of 2 to the n, that goes to infinity. So this diverges by the nth term test. It's good to write down what test you're using when you do this sort of things. All right, this guy. If we take the limit as n goes to infinity of n factorial over 2 to the n factorial, or 2n factorial plus 1, this plus 1 is not going to matter when we're going to n factorial. So we'll have n factorial over 2n factorial. The n factorials will cancel. We'll get 1/2. All right, so the limit goes to 1/2 of this sequence in here, but that just means that this limit of the sequence is not 0. That's not 0. That means at the end of this, we'll keep adding 1/2s over and over and over again, which means it will diverges by the nth term test. All right, what about this last one? So we take the limit as n goes to infinity of 1 over n. Well, that's clearly going to 0, but if it goes to 0, that tells us nothing. See, if the limit goes to 0, that does not mean it converges. So we're left here not knowing. It could diverge, or it could converge. All right, it actually diverges. Strange that that's like the smallest thing that will diverge just about that we can find. All right, so that is series introduction. We'll have some more tests for convergence and divergence in 9.2, but this is the end of 9.1, so check out the homework for 9.1.